This is practical number 4, analysis of Latin square design. In this first example, we are having a study is completed to find the work schedule that leads to the best job satisfaction for a group of technicians. 4 schedules were in the study. A is 4-day week, day shift. B is the treatment that is 4-day week, evening shift. C is the treatment that is 5-day week, day shift, and D treatment is 5-day week, evening shift. 4 technicians were available for the study and each used each work schedule for a week to help to control possible order effects. An LSD was employed. The data given in the table represents a job satisfaction score obtained from a questionnaire administered at the end of each week. Higher values indicates more satisfaction. This is the data we are having technician 1, 2, 3, 4, their week 1, 2, 3, 4 that we are having. Analyze the data completely. Also find pairs of treatment which differ significantly using CD. So here, if a single observation is made per experimental unit, then the linear additive model is xijk equal to mu plus alpha I plus beta j plus gamma k plus epsilon ijk, where ijk belongs to S, where mu is the general mean effect, alpha I, beta j, gamma k are the effects due to ith row, jth column and kth treatment respectively. Epsilon ijk is the error effect and is assumed to be normally distributed with mean 0 and variance sigma I square, that is epsilon ijk follows normal 0 sigma I square IID. We are having notations like this. TOSS is for total sum of square, TRSS for treatment sum of square, RSS for row sum of square, CSS for column sum of square and ESS for error sum of square. Here we are testing 3 hypotheses: H naught R alpha 1 equal to alpha 2 equal to alpha 4 equal to 0. H1 R at least 2 of the alpha is row means are different. H naught C beta 1 equal to beta 2 equal to beta 4 equal to 0, or H1C here we are having at least 2 of the beta j's column means are different here. And similarly H naught of T gamma 1 equal to gamma 2 equal to gamma 4 equal to 0, and here H1C here H1C actually here at least 2 of the gamma k's treatment means are different. So this data we are having, what we have done here, we have taken row sums here, this 18 plus 7 plus 13 plus 10 like this here row sums. Similarly column sums are taken here, their squares also obtained here, their sums are also taken here. Here also square of this 48 is taken and its sum is obtained here. So this is row sum and its square we have obtained, column sum its square we have obtained. Similarly here what we required for obtaining treatment sum of square, we have written here treatments A, B, C, D and their values we have taken here row wise here. Treatment A here in the first row it has value 13, just see this one, treatment A has value 13, so that we have taken here. In the second row treatment A has value 15, here we have taken. In third row A has value 18, we have taken this, and in fourth row value of A is 13 here, that we have taken here. Such a way all this treatments their values taken row wise here, and we have written here its total we have obtained here. This is the total of all observations. Its square we have obtained here, tk square here, that sum also we have obtained. To get total sum of square we require sum of squares of all the observations. So here squared this 18 square, 7 square like this, all this 16 observation their squares, their total we have taken, that total we are having this one 2124. Then Ri is sum of ith row, Cj is sum of jth column and Tk is sum of observations receiving kth treatment. We have taken those notations in the previous table. So we obtain firstly CF correction factor, that is G square upon N. G is here 174. Total we are having as 174. Its square divided by total number of observations 16. We will get this value. Total sum of square is summation of xijk square over triple values here, triple sum actually, minus CF, and that we are having this sum is this one here, 2124 minus that CF we have obtained here. So subtracted, we'll get this as the total sum of square. Treatment sum of square can be obtained 1 upon m summation tk square minus cf. So we'll have this tk square sum, that is this value we have taken, and 1 by 4, 1 upon m is 1 by 4 minus cf is this value. So we get this as treatment sum of square. Similarly, row sum of square summation of ri square, that value is this value here, 7602. This divided by 4 minus cf is this value. Column sum of square 1 upon m summation cj square minus cm. Summation cj square value is this value, cj square, its total we are having, divided by 4 minus cf, this gives us this value here, and from all this value we obtain error sum of square, that is by subtraction total sum of square minus treatment minus row minus column sum of square, we will get this as the error sum of square. So after getting all these values, we put this information in the table. ANOVA table, we are having general ANOVA table like this here. Sources of variation, we are having rows, column, treatment, error and total here. Their corresponding degrees of freedom, m minus 1, m minus 1, m minus 1 into m minus 2 here, and total degrees of freedom is n square minus 1 here. Their corresponding sum of square, mean sum of squares, and corresponding F ratios we are having here. Corresponding F ratios we are having here. So substituted all those values what we have obtained in the previous. M is 4, so we'll get here degrees of freedom related to row 333 here. Error degrees of freedom is m minus 1 into m minus 2, it becomes 6, and total 16 observations, so total degrees of freedom 15 here. Corresponding sum of square what we have obtained here, those we have put here all this information, and dividing this sum of square by degrees of freedom will get me sum of squares here. Then taking here F ratio, how to take F ratio, this mean sum of square divided by error mean sum of square here. If this ratio comes out less than 1 here, this, see here in the first case we are getting less than 1, so we will take 1 upon F here, so this divided by this. So because of that its degrees of freedom also changes here. So we have seen here value for 6.3 instead of 3.6 we have taken 4.63, this F table value. Here we are getting the ratio, this one is larger than this one, so the ratio we have obtained usual way. Here also we are getting the ratio usual way here, so because of that we are having this as 4.75, 4.75. So if we take decision here, this is less than this, so hypothesis accepted. Here also accepted means for rows and column it gets accepted, but here in case of treatment this is larger than this one, so for treatment it gets rejected here. So we have written from this, since FR less than F63, FC less than F36, we accept H naught R and H naught C at 5% level of significance, that is row means and column means do not differ significantly, but FTR it is greater than F36 here, so we reject H naught T at 5% level of significance, that is treatment means differ significantly. So after this we'll go for the critical difference method, which because of which pair of treatment means we are getting this, that hypothesis gets rejected, that we obtain by using this critical difference method. So find pair of treatments which differ significantly using CD here. So we are having this CD between any two treatment means TP and TQ at level of significance alpha is given by CD. TP minus TQ is equal to critical value of T at level of significance alpha for 2 TELD into square root of 2 MSSE upon M here. So here when we are considering this is at error degrees of freedom we are having, so here we are having error degrees of freedom as M minus 1 into M minus 2 alpha by 2, we'll see this value. So that degrees of freedom we are having 6 and 0.05 by 2 here for 5%. That value we are having this value here, square root of 2 into MSSE upon M. M is 4 here, MSSE, this value we are having this here 4.5833. So that value we have used here. So we get finally this value as this value. Then we'll have this decision rule. If Absolute value of TP minus TQ means the corresponding treatment means actually here. This is greater than CD TP minus TQ means this value. P not equal to Q, I that is equal to 1 to M. Then P and Q treatment means differ significantly, otherwise not. So we have taken this, these are the treatments here. Their corresponding means we are having here 14.75, 39, 9.5 and 9.25. How we get these values here? From this value here we are having here treatment totals here. These totals we are having, divide this by 4 because total number of treatments is 4. Divide this total by 4, we'll get this values here. And here pair of treatment means we'll take here 1 2 pair we have taken here. So take subtraction of 14.75 minus 13 and its absolute value, that is 1.75. Likewise we have done this differences here for all. CD remains same because the number of observations are same here. So we'll compare this with this values. If this is larger than this one, then we say that it is insignificant. It is significant here. If this difference, absolute value of this difference is larger than this one, then it is significant, otherwise not here. So this is less than this one, so insignificant, here greater than, so significant, greater than, significant, less than, so it is insignificant here. This is greater than here, significant, and this is less than, so it is insignificant. So which pairs we are getting, that will write after this here. Since the difference TP minus TQ for the treatment combinations AC, AD and BD. See this one AC, AC, AD here, this two, they are significant here, and this one B and D, second and fourth treatment means B and D differ significantly, and the other treatment combinations AB, this one AB, BC, BC means this value, second and third means BC, and CD, CD means this one here. This third and fourth treatment means CD is, it do not differ significantly. So such a way to complete this. This is the second example. Here we are having 5 treatments and 5 rows and 5 columns here. Same way you have to perform this here.